I'm very delighted, of course, to welcome one of our prominent speaker here, Dr. Samuel H. Moseley. He normally goes by the name Harvey, a senior Goddard astrophysicist. Colleagues such as Nicholas White, the former director of the Earth Sciences and Exploration Director at NASA Goddard, used to describe Harvey as a genius in conceiving and realizing new technologies that have been used in some of NASA's most successful space missions, such as COBE. We all know COBE, which led to the Nobel Prize by John Mather and others. And then the Space Infrared Observatory Spitzer, and of course, James Webb Space Telescope, all of which have enabled or will enable revolutionary new science and profoundly change our understanding of the universe. Today, Harvey is supposed to talk about a little bit of his journey, but more importantly, he's going to tell us about the work that he and his team have been doing on designing a new instrument called HIRMES, High Resolution Mid-Infrared Spectrometer, an instrument that will be used to probe the inner secrets of what they call the protoplanetary disk, where the solids materials on a very short time scale are separated from the gas to allow the coalescence of planets. So ladies and gentlemen, without further ado, help me welcome our speaker, Ari Moseley.
It's a little bit different than advertised. I'm going to spend a little bit of time talking about the Hermes Instrument, which is what we're doing now, and then I'm going to do a description of the sort of random path that got me to actually doing Hermes, and random it is. Okay, well, Hermes is a high-resolution spectrometer that we're developing for the Sophia Observatory. It was selected for as a third generation instrument for Sophia, and is planned to fly in a little over a year now, so it's coming down quickly. We were asked to develop this thing in about 2.5 years, and given that it's as complicated an instrument, I think, as anybody has ever built around here, it's a very challenging thing, and we have a lot of our Hermes colleagues here, and they know what I'm talking about. The primary science, as I say, is to investigate protoplanetary disk physics, to tell something about how does the mass evolve during planetary formation. It's really shocking. I didn't know much about this when we started out, but when disks form around stars during the early formation of planetary systems, the gas and the dust is all hooked together, but then at some point the gas gets dense enough to provide viscous damping, and all the grains fall to the center line. And by gosh, once it settles down, they start colliding, and the entire solids in the system are basically eaten in about 10 million years. So it's a very rapid process. And during that time, essentially all the solid material in the system disappears. So we're going to try to measure this. We want to know how the oxygen, water ice, and water vapor are distributed in the systems. We believe that water ice is a critical component for the formation of giant planets. So you're not going to make giant planets inside of sort of an ice line. And then we want to know the distribution of these things, and then we want to know the kinematics. And finally, we want to actually get the mass of these systems, and we can use the isotopic analog of molecular hydrogen, HD, to do that. So we're trying to figure out how these systems evolve. The problem with this, as we have a system that starts where things are coalescing, they have ice in them, and they have gas in them. Both of them are hard to observe when they're cold, and this actually makes it very hard to test models. So we're building an instrument that can go after both the ice and a dominant mass constituent of the gas. So for the water and the ice, we have lots and lots of rotational lines of water, and even some relatively low-lying lines that can probe modest temperature ranges. In addition to this, water ice has some strong features in the 40 micron range and then at 63 microns. So we can determine the amount of water ice that's in small grains. Once it all gets crunched into planets, it becomes pretty invisible, so you should actually see these things disappear over time as they come together. The water vapor, of course, is going to tell us what's going on around the snow line in these systems, inside of which you're primarily gaseous and outside of which you're solid. And so there are lines all over that have different excitation energies above the ground state. So we're trying to get ones that are relatively cold so that we won't be so temperature sensitive in trying to do it, and we've identified some nice ones for that. Neutral oxygen is going to be a very strong line, so we can use it as an effective way to get kinematics to give us information on radial structure, but it's also a good structure. It's also a good probe of the oxygen abundance, that's being a dominant heavy element. And then finally, HD is has this 112 micron line. The interesting thing is that you'd say, well, why don't you just do molecular hydrogen? Well, the problem is the ground state line of molecular hydrogen is at 28 microns, and the systems just aren't warm enough to excite that line to any degree. So the fact that this line is low-lying, it only has 112 micron excitation energy, is pretty good. The other thing, though, is you'd say, well, isn't the very low abundance of deuterium going to screw you up in this thing? And the answer is not so much, because the asymmetry caused by the mass difference between hydrogen and deuterium, that increase in effective dipole moment that you get from that increases the transition probabilities for this by about the same factor as the abundance of deuterium. So it's going to be, under equal conditions, it's going to be just about as bright. And so we want to be able to, even though these hydrogen lines can exist far out in the system, we want to be able to resolve those lines so that we can actually determine where in the system they're coming from. So we need to have velocity information on them, so we're going after them with pretty high resolving power. And so you see this is a cross-section of a disk, and you see the system is beginning to settle out. But the idea is that we can get the water vapor from the surface of that. You can think of that whole surface as sort of an atmosphere above which you have all the vapor phase stuff. And then in the inside, we'll be able to see the molecular hydrogen and the water ice and so forth. So we have a pretty good tool for it. But in order to do this, we need to have an instrument that can work over about the 25 to 125 micron range, and we need resolving powers that are up to about 100,000. So this is different than instruments we've built in the past. We have identified a number of lines that look, these are the water lines. We found some nice ones that are doable. There are a lot of nice ones from space, but when you're doing water vapor in the Earth's atmosphere, you have to find ones that don't collide with the water vapor features in there. So we think that the spatial distributions, we think we're going to be able to determine by the rotational velocities, and we expect the water vapor and the oxygen to be biased to the inside, the water vapor in particular, and then we expect the HD to be on the outside. And by looking at the differences at the shape of the line, we should be able to tell where the material is coming from in the system. Finally, the water ice water has a strong feature in its spectrum, and crystalline water ice has another one at 63 microns. We discovered both of these features, at least in celestial sources, with our instrument on the Kuiper Airborne Observatory, and it turns out it's a nice probe for water ice, and there's lots of water ice around, so we think this is going to be pretty good. We have a whole additional bunch of measurements we can do on star formation, and then other general, there's going to be a whole range of galactic astronomy that can be done with this thing, and so we're planning to enable that, but we're designing it to be well suited to the protoplanetary disk. And the reason for that is we said, okay, what are the big questions out there in astronomy? And then you say, which are the ones that Sophia has a chance to contribute to? And so it looked like to us that this was almost a unique intersection on this one, so that's where we ended up on this. And just to be clear how we're going to do it, we're going to have a high resolution mode that'll go up to 100,000, and then we'll have a grading mode low res mode that will let us do the continuum spectrum to get the information on the water ice and so forth. We're using background limited bolometers. We've developed detectors over the last 40 years working. My group working with the Code 553 detector branch have developed an excellent capability for that. So we're using devices produced there to provide high performance detectors. And then we've teamed with Gordon Stacy at Cornell, who has 35 years experience making Fabry-Perot interferometers for cryogenic systems, so that we are sort of ready to, we believe we have all the pieces covered now, and we're sort of ready to go. Okay, so I'm going to just talk now about, and by the way, parts are coming in now. We have an optical bench that'll be delivered soon. We hope to be testing in the fall, and we hope to begin commissioning about a year from March, so this is going quickly. Okay, well, Hermes is a large and complex cryogenic spectrometer operating in the far infrared. It requires lots of specialized techniques and technologies. Lots of specialized techniques and technologies are required to build such an instrument. And I've had a long history of developing increasingly complex instruments, and like I say, almost by chance, my grad school years provided me with a real apprenticeship where I had the resources and independence, where I actually was able to learn how to develop instruments to address science questions. But I'm going to back up a little bit and give you some biographical background on this stuff. When I was 16 or 17, working with my girlfriend, now wife, Sarah, and another friend, Tom, we built an observatory with a 12.5-inch telescope. I ground and polished the mirror and the whole business, and this was my first experience with project management. We actually did a pretty nice job. We built this and got it in pretty good shape, but then it was time to go off to school. So off to college, and I ended up going to a formerly all-girls school with my girlfriend, now wife. Went to Connecticut College, small liberal arts school. There were 1,400 girls and 11 guys when I went there. So it was a different experience. They did not have very many physics students. And especially then, they had even fewer who knew enough math to actually jump in at that time. So I basically got tutored by the physics department because I actually knew some math when I got there and so forth, and was a math major. So I sort of got tutored, and then so I stayed there. I stayed there for 3 years, and then off to University of Chicago, and I almost didn't make it. This is sometimes I don't get everything in just on time. And I had put in a bunch of applications, and I had sent my GRE scores and stuff to Chicago, and it indicated I was going to apply, but somehow I didn't actually end up getting it in. And so I got a phone call one day, and I don't know how people used to get phone calls in the old days when there weren't cell phones, but somehow somebody called me and they were able to find me near the telephone and so forth. And it was Bob Odell, who later he was the chair of the department at Chicago, and he later became the project scientist, I guess, for HST. But he called up and he said, well, that he wanted to know if I was still interested in applying. And I said, yeah, yeah, I would like to do that. And he said, well, you're in Connecticut, right? And I said, yeah. He said, well, I'm going to be driving from Boston to New York. How about I stop by and pick it up? So he actually came by and picked up my, came by and picked up my application, and I, in fact, did get admitted. And I, in fact, did go to Chicago, but it was a near thing. So you never know. Here's a picture from the depths of time here. This is my observatory from 68, I guess. And that's the 12.5-inch telescope there we built. We have cast concrete for all the support structures. You see our oxygen settling set up on the left there. And so we were set up and ready to go in those days. So we were ready to proceed. It actually worked reasonably well. So I went to Chicago, and my first job there I was a grad student on a program for the Large Space Telescope. That was what Hubble was before it became 2.4 meter. It was 3 meters in those days, and then they decided that 2.4 meters wasn't large, so it just became the Hubble Space Telescope. But I was doing precision astrometry with that, but my professor from there ended up going to Yale to be department chair there, and I went for a couple of months. And I said I didn't think I wanted to do that. So I joined the far infrared group and went back to Chicago. So that's random event number one. Actually, it's probably about 500 random events before that, but that's okay. Al Harper at Chicago had started a far infrared astronomy group. He was a grad student of Frank Lowe and was flying on the NASA Learjet. I guess Frank had really brought all the low temperature detectors to astronomy and the bolometers, and so enabled the long wavelength observations. We were observing between, say, 30 and 300 microns. So I joined Al was working mostly with the Learjet to begin with, and then transitioned to the Kuiper Airborne Observatory. I joined the group with students Harley Thronson, who you guys know here at Goddard, and Charlie Telesco, who's now at the University of Florida. And we were able to build a bunch of instruments on the KAO that it really did enable a pretty wide range of exciting science. It was mostly far-hour imaging, but in the later years, Roger Hildebrand, who had been a high-energy physicist, moved into and started working with us and developed polarimeters with students Stan Whitcomb and Jocelyn Keene. Stan became one of the leaders of LIGO. He left and took a job he got a faculty job at Caltech out of grad school there. And I said, well, you're going pretty far afield with gravitational waves, aren't you? He said, well, no, I'm still in the boson business. So he said he didn't think it was so far. But early on, we were flying the Learjet. On the left is Harley Thronson operating the instrument rack. You have to sit against the door, and the rack's up against the right wall there. You're seeing the pilot's helmet right beside him right there. And then on the right-hand side is Bob Lowenstein. He was back here. The telescope stuck out. It didn't stick out, but it went through a penetration on the side of the plane right off of Harley's right shoulder. So Bob was there. You had to take off with the thing almost in your lap. So as some sort of concession to safety, they made that person wear a helmet. I think it would smash your face, though. Okay, now we're going to start on a number of the, this is part of my Ravages of Time series. You get to see what time can do to people. Don't ever let this happen to you. This is from mid-1970s. This is me working on a helium storage doer. But we developed several generations of far-infrared photometers and imagers. And during that time, the computer technology needed to run these experiments. We started out, I think our earliest one on the KAO was a Hewlett-Packard desk calculator that you could actually buy you could buy digital interface cards for it. They weren't terribly fast, but they would work. So we did that. But then in the mid-70s, all of the microcomputers came on. So we got those things and had them up and running. But there were no languages for them then, so everything was, there were no languages, no drivers, no nothing. So everything was assembly language, and you had to talk to the hardware and so forth. So it was, we spent a lot of time doing that. At Chicago and then later at Goddard, my career strategy was, I don't think I would recommend it in general, which was look around and see what needs to be done and do it. And if you've got a decent project going, that's not a bad one, but I think you need to spend a little bit more time picking the projects maybe. I did make one decision. Up until 1977, I had done almost all the assembly language programming for the data systems and all the hardware for the interfaces. And I made a decision not to continue with that, with so much computer stuff, because there were lots of other things that needed doing. Bob Lowenstein was interested in doing it. And number three, I knew I could get addicted to it, and I knew that that wouldn't be good. So I kind of gave that up. And as we said in those days, somebody could probably make some money with these computers, but we never did anything about it. Okay, so we built these instruments and ended up doing a lot of flying on the Kuiper Airborne Observatory. Here's some pictures from the, I think this is probably 70s. That's our friend Bob Lowenstein in the back. We were doing this. We built all this stuff too. We never. My advisor thought that we could build stuff cheaper than we could buy stuff because we were doing large numbers of channels of things, and he was probably right. But it meant we had to build everything, so we did that. On the far left in the back there, that's Bob Garrett's there, so a number of people flew with us in those days. Well, the way I felt about it, and as I was coming along, was that this really was a little bit of the blind leading the blind. Everything we were taking as ancient lore here, we realized was something that somebody had dreamed up about 2 years before, you know, so there was almost no basis of knowledge about how to do this stuff. So we were actually sort of making it all up as we went. But of course, we didn't understand that at the time. We thought we were evolutionarily changing some well-established set of techniques, but they actually didn't exist at the time. So here's the group of people from those days. We kept in the back, there's me over on the left side, in front Bob Lowenstein, beside me Al Harper, my advisor, Roger Hildebrand, and then Ed Shea, who's maybe at Maryland now. But that team stayed together for a long time, so they were able to, it made it possible to actually do a lot of stuff and do it very quickly, because you had very, very experienced people doing it. And this is, we are looking at the instrument on the telescope here. This is one of the, this must have been in the 70s also. And that's Jocelyn Keene, who's later at IPAC, and me. She was one of the first people working on far infrared polarimetry. Well, we ended up being the first people out there in a new field like this. You get to do lots and lots of things that are really obvious, and you can get good, really interesting results to begin with. The sorts of things that we found when we were doing that was we discovered the internal heat sources of Uranus and Neptune and characterized those. We did the first far infrared millimeter studies of the galactic center, where you're starting to first get a sense of how much stuff is around it. And then Harley Thronson did the first surveys of H2 regions in the far infrared, where you were starting to learn that the dominant source of radiation, the far infrared is a dominant path of radiation out of a lot of those systems. And then I worked on late stages of stellar evolution, looking at planetary nebulae, and you can actually see the dust that forms in the system and the dependence of it on the chemistry of the systems they're in and so forth. But as I say, we had a team that stayed together for a long time. Wasn't a really big team, but everybody knew what they were doing, so it was really pretty good. Here's the team. Third from the left is Stan Whitcomb. He's the senior LIGO guy now. Beside him, Al Harper. That's me in the back. Harley next to the right, and then Bob Pernick, who was the engineer for our group. And this group basically did this stuff. So, following the completion of my thesis, I came to Goddard, and well, let me tell you first that while we're talking about the things we got out of the K-Air, let me give you a science pitch first. After coming to Goddard, we built a number of far infrared spectrometers to follow up on some of this stuff. We found a number of interesting things. A couple of years before the Voyagers got to Uranus and Neptune, we were able to get vertical temperature profiles in the atmosphere. So we got we were able to nail down the atmospheric thermal structure with that. The 43 micron water ice feature, emission feature, that we want to use for disk characterization now with Hermes, we actually did the initial detection of that one in some stellar outflows. So, and we were able to show that the ice was crystalline, and it's actually amazing. You can even tell whether since it's crystalline, you can even tell whether it's oblate or prolate, which is an interesting thing. We had the good luck that the only nearby supernova in the last 400 years went off while we had an instrument up and flying, so we were able to do spectra and get the newly synthesized elements in supernova 87A and measure the thermal evolution of it as it expanded. And we also did, following that, we did the Cas A supernova remnant to look at the dust in that, which was interesting for comparison. And then we discovered exotic dust in the galactic center. One of a Maryland student was working with me on that, and it was a very interesting result. There's a strong chemical signature of the dust in the circumnuclear ring in the galactic center, and I thought it was a really interesting result. But it's very interesting because you cannot get any of this is so strange. The people who do this, who do galactic center stuff, never cite this, and it's an absolutely interesting result, and I have no idea why. I have no idea why. It's a perfectly sound result. Just to give you a sense, these first generation instruments were typically tiny. The outside stuff, all the readout electronics and stuff, was about the same size as now, but the instruments themselves are pretty small. Here's a detector. The light goes in here, goes here, off a grating, back off another reflector and into the detector. So it's a Roland spectrometer. And we flew this for a long time. It was 30 to 50 microns. That was the first instrument that I built when I came to Goddard. And it was to build instruments like this that I started with working with the group in Building 11, and we started up the production of low temperature thermal detectors for that. So we started off with things where they would put electrical contacts on it, and I would do all the handicraft with tweezers and put them together and assemble them. And then after a while, we started micro machining the things and so on. So it's not like the guys started out building huge arrays and everything worked great. It was very incremental and so on as we went with that. And here's another, we got Bob Silverberg, Ellie Dweck, and Bill Glackham, who was another student of us. So now we can, in a little bit reverse order, I'm arriving at Goddard. I arrived at Goddard as an NRC postdoc on the 10th of October, 1979, to 3 inches of snow. It's the earliest snowfall here, earliest measurable snowfall by over a month. And I was looking forward to the temperate mid-Atlantic climate here. But I had a grant to build that little spectrometer for the KAO and started to work on COBE. And again, much of the infrastructure that we developed for the KAO work, the detector production, testing, and so forth, ultimately became the stuff that was used on the COBE instruments. The detectors were built over in the cryo branch, but they all used the same doped semiconductor chips, thermometer chips, and stuff that we had developed for the KAO work. I got hired on the staff here in August 1980, largely because of widespread fear of an upcoming hiring freeze. Nothing like the fear of a hiring freeze to get them to actually move on something. But through good luck, I found myself in the midst of this really spectacularly talented team of people that was put together for COBE. And I spent the next years basically walking around the center, keeping track of all the instrument systems for the COBE instruments that were being developed. And very early, I recognized that there were things that we could do well because of facilities and staff, and that there were other things that we were terrible at. And I realized that getting around the bad parts was going to be the primary challenge of It used to be that if you tried to go through any of the internal fabrication sources, it would take forever. It used to be procurement took forever. So you needed to have alternative paths for all that stuff. And like I say, and as you know, Kobe came out all right. It did all right. As you look now, we were, after I'd been here a few years, Frank McDonald challenged the X-ray group to look for ways to improve non-dispersive spectroscopy above the performance that they could get with the silicon diodes. And this was largely in anticipation of the call for instruments for the AXAF facility, now Chandra, which ultimately came out in 1984. So they were thinking maybe they could use smaller band gap semiconductors, and they knew we were using indium antimonide devices. So thought that it might be good. So Rich Mashatsky came down. He explained the problem, and I said I didn't know about the INSBE, but it turned out I had already done the calculation for low temperature thermal detectors because somebody had asked me about the sensitivity to laser pulses, and it was the same problem. And I had it in my drawer, and I found it. So that's the only time that's ever happened in my life. But that was But I asked him if 1eV would be good, and he said yes, that 1eV would be good since they were getting about 130 EV at 6K EV. The rest is history, and that history's mostly been made by the X-ray team at Goddard, along with Dan McCammon at Wisconsin. During the 80s, the team was Rich Kelly. Rich Kelly and Andy Smkowiak were both postdocs and started. Steve Holt was director of sciences, and he assigned those two guys to work with me. And we started building up experiments and so forth. Dan McCammon came and spent a summer here, and we developed we developed the system and did all the measurements for the first papers on this stuff. And Rob Scholkopf, who's now a big shaker and mover in quantum computing, worked with us during that time, and we were trying to bring the calorimeters to TRL-6 and to get the higher performance as part of the AXAF mission. Around 1990, Rich took over as PI, and Caroline Kilborn and Scott Porter came in to work and have been the sort of driving force behind the various astro instruments. And they brought in the rest of the team, Simon Bandler and Steve Smith. I mean, it's just a really strong team there, and they've done an excellent job on that. This is the first spectrum that we have. On the left there, in the inset, you see the response of one of our detectors to a single iron 55 photon. And in the bottom, you see a pulsar over at 0 energy. And then this is iron 55 K alpha, and this is K beta. So this is the spectrum for our first paper here. This was actually worse than the performance of a silicon diode, but it was very encouraging because it was exactly what we predicted it would be for this detector. So it gave us a strong indication we were headed in the right direction. So this is sort of what got us going. This was an improved version of this was what went into the AXAF proposal and actually what got us selected. So that was this was, everybody says you have to fly stuff that's completely mature. And I have at least 2 counterexamples to that. With these, by the time we flew them, they were pretty mature, but for selection, we actually did get this done. As the various politics of X-ray astronomy evolved, we were asked to move on to take the spectrometer instrument and put it onto the Japanese to team with the Japanese and put it on theirs. That hadn't worked out that great in a number of ways. They had a failure to the launch the first time. They had a failure with the cryo system the second time, and they had an operational error the third time. So we're hoping fourth time is a charm right now. But nonetheless, here's a spectrum taken with the microcalorimeters. These things, when we proposed AXAF, we said we were going to produce 12 EV. This instrument is a little over 4 EV now, the one that flew for a month until the operational error killed it. But these papers, it's gotten a couple of Nature papers out of the first observations, which is very impressive. You can get, you see these lines of different ionization stages of nickel and iron, so you can actually get lots and lots of information about both composition and ionization balance in the systems. And by the width of these lines, you can determine how much pressure you have and how much kinetic motion you have and so forth. So it's a pretty remarkable system. So anyway, this is coming along, and this is something that everybody uses now. The L2 instrument for the L2 mission for ESA is Athena, which is a high resolution, is a spectroscopy instrument, and they're going to use a high resolution microcalorimeter. The goal on that one is to have 2 EV resolving power over the entire array, and the detectors are around now. The X-ray group has developed devices that produce that kind of performance now, so it's likely that that will happen. But that was one that I wouldn't have planned. JWST is another one that popped up, and I don't know that I would have expected that this is something I would have normally worked on. But a call went out for instrument concepts, and we put together a team to develop a concept with Bruce Woodgate being a principal player. Bruce would always come by my office and always have some interesting new clipping or some interesting new idea on things. So Bruce said, hey, let's do it. And so we put together a proposal for a multi-object spectrograph. And we've had some technology workshops, and everyone recognized the need for a field selector to produce a multi-object spectrograph for JWST. However, in the negotiations with ESA, ESA got the near-infrared spectrometer, but they recognized that they needed a field selector as well. So anyway, at the same time, a call for technology came out, and I didn't plan to apply, but Bruce did. I looked at the concept that he was doing, and I thought it looked extremely hard, and I suggested something like the current JWST microshutters instead. Bruce liked it, but he said, why don't you be the PI? And so that's how I ended up doing the microshutters. So we were trying to come up with shutters, and the idea there is to be able to take a field like the upper left and then to be able to open for the spectrometer all of the relevant slits for the objects. Here's a single pixel. This is 100 by 200 microns. This is a long torsion bar, and the way we do it is these are magnetic stripes, so we run a little magnet over it, pulls it open, and we electrostatically hold them, and then we drop the ones that we don't want. So it's not the way you would choose to do it, but it's the way you do it when you're required to invent on schedule. So it's, you do the first thing that works. And here's the system getting ready to go in. These are 4 quadrants of microshutters. The rest of this is support structure, readout electronics, and the scanning mechanism for the magnet. Okay, so I guess at this point, where we are now is it sort of brings us up to the present in a lot of ways. We are trying to build right now the Hermes instrument. It's a complicated instrument, as I said. It has filter wheels, Fabry-Perot wheels, slit wheels, high-res, mid-res Fabry-Perots, and then it has detectors optimized for different wavelength operations and so forth. And it has to be this way to what the biggest challenge in using the SOFIA thing is. It's a high background instrument, and since it's a high background facility, and sensitivity is an issue. So you have to go through and do essentially the best job you can do to get as much sensitivity out of it. So we had to do this. We need detectors that have efficiencies between 50 and 90%. And they have to all be strongly background limited and so forth. So we're doing that. The lessons learned from years of building instruments, as we said, hey, those Fabry-Perots don't seem that easy. So we said, let's find somebody who knows how to do it. So we got another old KAO guy, Gordon Stacy at Cornell, to do it. And he already had a bunch of these Fabry-Perot systems sitting around the lab. And they've developed these for doing it. By the way, for you who are working on OST, this is this was the instrument for Matt Bradford's thesis. So, and these are the designs we have. We're just using, this is about as old school as you get. We're just using metal mesh mirrors and so forth like that. But they did a really good job, and for the proposal, they set one of these up on the bench and demonstrated the R of 100,000 spectroscopy with it. So that was a big one because people wanted to see that, I think, primarily because it sounded like a big number. But that was it got they went ahead and did it. As I said, right now our guys in Building 11, led by Ari Brown, have built the detectors. We have a low resolution array that's 16 by 64 that allows us to read out a grating with a long slit, so we get 16 spatial positions along the slit and 64 spectral positions, and we can tune it up. For doing high resolution spectroscopy, we use these detector arrays. We go to ones that match in size the diffraction image at the wavelength, and then each one of these things has a resonant back short at that approximate wavelength. So we get, the goal is to have above 90% absorptivity for those and near optimal pixel size for it. So this detector is almost done. We have an engineering version of this one. This one, we have a few more demos to show that it's right, but we believe this is pretty close. And the way to fan out all of these detectors to the readout has all been developed. The instrument is coming together now. We have the optical bench with all the mirrors on it, and I'm sorry I don't have the picture for that now, but that already is in place. It exists and will be here very soon. That's being built by Space Dynamics Lab at Utah State. And we should get that in the next weeks, I think. And we'll be testing that here at Goddard. The cryostat will be coming in another month or two. And then we have, you look at our schedule and it goes like this, and we're pouring all this stuff into this cryostat now. So the idea is to be testing this thing in the fall and be ready to ship it out to California in March-ish next year. So that's where we stand. So even though I was an amateur project manager as amateur project manager as a teenager, I'm glad to have real project managers for this one, because making all this stuff go together, given the scale of this instrument, the complexity, and the schedule we have, really does require constant attention at making the stuff happen. So I think that's my story now. And if you guys want to ask me questions about all these key and insightful decisions I made along my life, I'd be willing to discuss any of those with you. But anyway, thanks for coming out. Bye-bye.
Okay, we'll take a few questions or comments.
What is the NEFD for your detectors for Hermes?
They are the question is, what is the NEFD? We have it's really high. The background's huge. It's for the spectrometer part, we can get spectral ranges of 20% or 30% with about 0.04 Janskys in an hour. And that's with resolving power of hundreds. And then the spectrometer, the requirement we have on the spectrometer is that we, at the R of 100,000, we have 10 to the minus 17 watts per root hertz, 5 sigma in 1 hour. So we can, the things that OST will be looking at out to 1 to 2 kiloparsec, we can see the nearest examples of them.
Okay. Yep.
Do you already have observational targets selected?
We have some observational targets selected, but they're sort of notional ones. We'll review them again, but we have existence proof that there are objects that have the properties we want that are bright enough to look at. We'll review that later and see if any new insights have come up, but yeah. Yep.
So you have mentioned randomness and luck
Yes.
quite a number of times.
Yeah.
So I'm just wondering if you could estimate the role of funding and politics.
Yeah, I don't know. For the answer, so the question was that what is the role of politics and funding in the thing? And the answer is that a lot of what I did was when I was a grad student, I wasn't terribly aware of that. We were sort of first out of the chute, so we got funded because they needed to run the observatory, and there wasn't anybody else that had instruments to do it, so we were in a pretty good position there. We ended up getting to do a lot of stuff early on just because we had instruments and nobody else did, and there was some money for that. Then and it wasn't huge amounts of money required for it. Then the first time we came into big money was the Kobe project. And yeah, I suppose there were real politics. That came out through an AO in which many mid-X's were selected, and they sort of worked down the list of them, and Kobe eventually got it. But you know, Kobe was pretty compelling science, and it did get selected, and then once selected, they did continue with it. And JWST had its own momentum, and we had for the field selectors, we had a competition with there were two competing micro mirror groups, and we developed for about 2 years and then went through a competition. And, you know, I guess if I were on the other side of that, I might have thought it was, you know, you might think it's political, but I think there was actually a sound reason for which they selected the shutters over the mirrors at that time. So I don't know. I mean, I feel like most of the stuff that I've done has either been too little or too big to get into too much into the where the details of the politics mattered. You know, either it was way beyond it was either way beyond what I was doing, or it was just you don't do this, you do something else later. But most of the things that I started on most of those things weren't funded when I started it. I remember with the microcalorimeters, Rich Mashotsky and I put in I came up with the basic idea in August of that year, and Rich and I put in a Director's Discretionary Fund proposal to actually do the demonstration on it, and we got $20K and went off and did it. That was, you know, so it was, back in those days, we didn't have to cover our salaries. So it was a whole lot easier to do that in those days. So, I don't know. It's, I think maybe my life has been charmed in that way. So, yeah.
Last one, yeah. Yeah, that's about.
Harvey, where do you think the next technical challenges to advance the science? I mean, because there have been a lot of technical challenges that you've faced. Where do you think the next tall pole is that you'd like to see come down?
Okay, so this is the general question about what the next tall poles are going to be, and I think that the things that people have identified as the tall poles for astrophysics anyway are correctly chosen. I know that building lightweight telescopes with good wavefront control and stuff like that, building large cryogenic telescopes, those are all big things. And then on top of that, you've got the detectors that have to be developed, and to really get the most, you know, we built detectors that were good enough to give us pretty much performance that's limited by natural backgrounds for broadband imaging now. But as we move to high resolution spectroscopy in space with cryogenic telescopes, we end up getting a few more orders of magnitude in sensitivity, and we're going to need detectors that can handle that. And so that's a challenge. And then for the things like the UV and optical, as well as perhaps mid-infrared, development of the micromechanical devices like shutters that needs to be made into a package that's much easier to use. And Mary Lee and her group have developed, now we have electrostatically addressed shutters, and those are scalable, I think, to the kinds of applications you want, but somebody has to keep going things. And the biggest challenge, of course, is that this is where the funding comes in. The biggest thing we have with the detectors is that it used to be you could do detector development in your lab on a small scale, but the challenge we have now is that the detector systems we're being asked to develop are enormous. And so it's a combination of large-scale engineering the large-scale arrays and doing the physics. So it's a tough combination, but it has to be done. So I think the fact that the scale of everything is getting so big, and then the other one is that the time scale for doing projects is getting so long that it's bumping up against the limits of the human lifespan. So that's, I think that is another really big problem, because you don't have time enough to both learn how to do something and do it in your lifetime. So anyway, okay.
So with that, let's thank Harvey one more time.